on the recording. So yeah, feel free to start whenever you.
Okay, yeah, thanks for inviting me and thanks for the introduction. Yeah, I'll be talking about MBL in tilted potential, and this is work in progress with these three people: Jad Halime, Achilles, and Evgeny Valev. I'll introduce first, yeah, some concepts about localization, and then the main question is, can it exist without quenched disorder? And then discuss measures of localization with results from the system we'll be considering. And then in a second part of the talk, I'll discuss a specific discrete symmetry of the system we are considering that seems to cause delocalization. And finally, we'll try to resolve this with results with existing results. And yeah, exactly. So generally, we expect a non-integrable interacting system to be thermalizing. Now, it's important to understand under which conditions this does not happen. And I'll be considering infinite temperature and the infinite time limit mostly for the rest of the talk. Now, to start, localization in non-interacting systems has been known for a long time. The prototypical example being Anderson localization of free electrons in a field of quenched disorder with local fields that have a quenched disorder. And there we know that the single particle eigenstates are exponentially localized, and the many-body spectrum of the system has no degeneracies. Now, an example of localization without interactions and without quenched disorder is Wannier-Stark localization, where the field, the local potential is just a linear field in the position of strength gamma. Here also the single particle eigenfunctions are exponentially localized, but due to this simple structure of the field, there are massive degeneracies in the many-body spectrum. So on the left here, you can see the single particle eigenfunctions being localized around the lattice sites for, this is a field strength of 2. And on the right-hand side, just for a small system, the many-body spectrum, where it's a bit difficult to see, but there are massive degeneracies at finite, at energies that correspond to a specific dipole moment, right? Multiples of the field strength. Now, in systems that have interactions, the almost 20 years ago, the concept of many-body localization has been introduced, and the prototypical example that has been studied in the literature is this kind of XXZ model with hopping interactions, both nearest neighbor and a local field. There should be a plus here. And for this system, for a disorder strength larger than some critical value, the system is expected to be localized even in the thermodynamic limit. That localization plays out in characteristics of the system as the following. For example, the starting from some typical initial state that's not an eigenstate of the system, we should have memory of that state even at asymptotically long times. If we start from weakly entangled states or quench the system into the disordered phase, we are expected to see logarithmic growth of entanglement entropy with time. Transport is of spin is absent in this system, and the level spacing statistics are Poissonian. All these statements are for this large disorder strength larger than some critical value. I'm not discussing here recent works that put this existence of a finite critical disorder strength into question. Yeah, but this is also not relevant in a sense for the rest of the talk. Now, if we replace the quenched disorder by the linear field from the Stark localization without interactions, and some additional term that could be either curvature or weak disorder, we observe phenomenology that it looks very much like many-body localization. So we observe, for example, for a Neal state, a finite magnetization imbalance. I will introduce that later. At asymptotic times, logarithmic growth of entanglement entropy has been shown as well. And a crossover from GOE to Poissonian level statistics has also been demonstrated numerically for as we increase the field strength. Yeah, so this ingredient here of perturbing the linear field by either a weak disorder or a curvature seems to be important. Some of the studies also consider the unperturbed case with a purely linear potential and find weak evidence of delocalization. Now, in this talk, I'll try to consider the case of a purely linear potential and ask whether many-body localization can exist there, and whether the try to understand better the prior results and that indicated delocalization, and yeah, try to understand this. If delocalization occurs there, try to understand better why this would be happening. I should also mention that prior studies found sub-Poissonian level statistics in the case of just a purely linear field, and an entanglement entropy growth which is faster compared to the case with some additional perturbation. And I'll fix units in the following as shown here. All right. Now, as I already mentioned, generically we expect systems to observe the eigenstate thermalization hypothesis with which means they should lose memory of the initial state at asymptotic times. And then in a non-thermalizing system, we should be able to see some memory of the initial state for typical initial states. Now we can always, in this, at least in this Stark field, we can always construct initial states which keep memory of the initial, which will not lose the memory, because the spectral bandwidth of the Hamiltonian is super extensive, and we can't. So if we take states from opposite edges of the spectrum, states with opposite dipole moment, which in a large field is the dominating term in the Hamiltonian, they have only contributions from states with that strong dipole moment and cannot be decay in a sense to something that looks like a state with a vanishing dipole moment, which it should if so states at that energy density of the initial state have a vanishing dipole moment. All right. Now, then the question one should ask is whether a typical initial state, so one with a small dipole moment, has finite memory. And an example that's often considered in the literature and in experiments is the Neal state with alternating, a product state with alternating spin up and spin down. And then the measure of the memory of that initial state is the imbalance, where we take the imbalance of the population in particle language at the difference between even and odd sides, and look at that as a function of time. So initially, or if you want the polarization between even sides and odd sides in the lattice. Initially for the Neal state, that measure is 1. And if the system is to thermalize, it should decay to 0. And if it's not thermalizing, it would decay to some non-zero value. Now, in the following, I'll show results, but I will not compute this quantity over the full lattice, but only over the central sites, where the central sides of the lattice in order to exclude boundary effects. Here I'm showing system size 19 with, sorry, all of the talk will be in one spatial dimension. And the field strength on the x-axis, so you can see that at weak field, we indeed observe decay of the imbalance to a value very close to 0. And then as we increase the field strength, the imbalance becomes finite. Now, in order to discuss whether the system is actually thermalizing or not, it's more important to consider how this behavior scales with the system size. So that is shown in the next plot. And you can see that, again, for weak field, we see the imbalance decaying as we go to larger systems. I'm showing even system sizes in the left panel, odd system sizes in the right panel. The reason for this will become clear in a few slides, but you can see there is no qualitative difference between the two. The lighter shades are weaker fields. Now, as we increase the field strength, the decay with the system size becomes slower to the point where arguably there is no change of the system size anymore for fields larger than 2. Okay, now let me move on to the next diagnostic of localization. That will be the level spacing statistics. And what is usually—
Benedikt, can I ask you a question?
Yes.
On the previous slide. So maybe so this is for just a tilt or tilt and—
This is, so all the results I'll be discussing are purely tilt, no additional disorder, no additional curvature. Yeah, sorry,
right, yeah,
that wasn't clear.
Thank you.
Yeah. All right. So the next, so the diagnostic for level spacing statistics is given by usually what is considered is the R value, which is the minimum of adjacent spacing divided by the maximum of adjacent spacings. And then the distribution of these values throughout the spectrum should follow this red curve here. If the system is thermalizing, this is a prediction from random matrix theory from the GOE ensemble. If the system is localized, we have the blue curve, so Poissonian statistics and absence of level repulsion. Okay. Now, this is what we see for the purely tilted case. The level spacings as a function, so the average of the level spacings as a function of field strength goes from something close to GOE to something very close to the Poisson value. I'm showing different system sizes here as well. Blue are the even system sizes, and red are the odd system sizes. No, I'm not arguing here for a certain finite size behavior. This is just to show that even and odd system sizes have very similar level spacing statistics, which is in contradiction with the sub-Poissonian level statistics previously observed for even system sizes, a contradiction I'll resolve in a bit. All right, now the last.
Do you have actual distributions, or?
I mean, I didn't plot them. They don't look as they don't look fully GOE, but they basically yeah. But I mean, it's a bit expected since the value isn't fully at the GOE expectation value. Yeah, sorry.
And can you say, so is this so this is an open chain, or?
This is an open chain, yeah.
And
so,
in some symmetry sector, or?
This is exactly, so I was going to comment on that later. This is the inversion symmetry that I'll introduce. This is within a given sector of inversion symmetry for the even system sizes. And this is for the sector closest to zero magnetization. So zero magnetization for even system sizes and one spin up or down for the odd system sizes. Okay. Now the last measure I'll discuss is spin transport, which is characterized by the two-time spin-spin correlation function. Well, I'm considering infinite temperature, and the measure for transport will usually be the second moment of that quantity, the mean square displacement. In a generic thermalizing non-integrable system, we expect diffusion. This is shown, what that would look like is shown here, just as a sketch. If the system is localized, this the spread should stop at some on some length scale, which is comparable or related at least to the localization length. Okay. Now, as I mentioned earlier, we'll be considering mostly infinite time quantities here. So the infinite time expectation value for the spin-spin correlator is expressed here. And I'm showing results in the bottom panel for now only for even system sizes. So you can see that as we increase the field strength, we go from a weak growth with this, or a growth with the system size, to a plateau or even a decrease, which is probably a finite size effect. Now, moving to even system sizes, we see radically different behavior. These are the blue symbols here, and these fully saturate the maximum possible value of the mean square displacement. These look like completely delocalized systems, and they show no dependence on the field strength. This is actually also holds at all energies in the spectrum. I'm showing here the mean square displacement at infinite time divided by the square of the system size against the bandwidth. And you can see that the we get a nice collapse of these curves as we increase the system size. Okay, so what we have seen so far is that at finite magnetization, so for odd system sizes, the Neal imbalance doesn't decay for large enough gamma. The level statistics look Poisson for large gamma. And the mean square displacement is localized for large enough gamma.
Sorry, did the previous plot have some curvature or not?
Curvature.
Why is the bandwidth scaled with L square?
In order to, sorry, not the bandwidth, but I mean, this is the energy divided by L squared, which is close to the bandwidth.
Yeah, so why are you dividing with the square if there's no curvature?
Sorry, because the bandwidth, the system, the bandwidth of the system itself grows as L squared, right? And so in order for this,
oh, I thought that was the case when you had the curvature.
No, sorry. If you have no curvature, but the tilt itself is creating a bandwidth of L squared.
Okay.
Does that make sense?
Yeah.
Yeah. Okay. Because the dipole moment goes in with the system size, right? Yeah. Okay. All right. So, however, at zero magnetization, we see drastically different behavior for the mean square displacement, while the other two measures are unchanged compared to the finite magnetization case. Okay. Now I'll move on and try to understand why this is happening. So the Hamiltonian we're considering has a inversion symmetry. What I mean by that is shown here. Inversion symmetry would mean spatial mirroring around the center of the lattice and flipping of all spins. And as well as the standard magnetization conservation. Yeah. Now, the inversion symmetry, when applied to some state, changes its magnetization to the opposite magnetization. So the two symmetries are incompatible in all sectors, but the zero magnetization sector. There they can coexist, and actually the inversion symmetry is a good quantum number in that sector for the eigenstates. In the finite magnetization sectors, the effect of this symmetry is that sectors of opposite magnetization have identical spectra, and the eigenstates at some energy are related to the eigenstate at the same energy in the opposite magnetization sector by the action of the symmetry. All right, so what does this imply for the mean square displacement at infinite time? Now, I separated here the two terms in the expression where the second term is actually completely model independent and basis independent. Sorry, alpha here is an eigenstate of the system. So the second term here is always order L squared, is a constant, just a function of the system size, and the sector one is in. So the term of interest is clearly the first, and assuming that there are no degeneracies, we can simplify this expression to the one below here. So a single sum over alpha. The apostrophe here should not be there. All right, now we can split the prefactor in front of the expectation values into even and odd terms. And by a simple change of some variable of summation, we can show that this term vanishes. So as I change from I to minus I, this term clearly stays the same. And now I can, through the inversion symmetry, I can replace SZ at minus I with minus SZI, which is the original expression except for the minus sign up front, which means that this term is vanishing. Now the remainder is has only this linear contribution here, and the only way that such a term in the infinite time average could contribute an order L squared contribution to cancel out the second term is if this average here was so the product, the average over all states, eigenstates, and their product of magnetizations with C as the center of the lattice needs to be of order 1 in the limit of the side being considered going far away from the center. However, this is clearly not the case in both delocalized and localized systems. So for non-interacting systems, you can show that analytically, and we verified this numerically as well, that this term is always of order 1 divided by L or smaller. This means that, let me switch back briefly, this term of order L squared will always dominate the infinite time mean square displacement, and thus the zero magnetization sector will appear delocalized in terms of this measure, unless there are a lot of degeneracies, in which case the simplification doesn't hold. So now, of course, now we need to verify whether there are a lot of degeneracies. What I'm showing here is the statistics of the spacing, just the energy between adjacent eigenvalues within a definite symmetry sector, so either odd or even. And clearly there is no eigenvalue, sorry, no spacings close to machine precision. Well, there is a many body level spacing which we can numerically resolve. This actually looks pretty much identical in finite magnetization sectors. Here I'm discussing the zero magnetization sector. Now, if we consider the spacing between states of opposite symmetry, or if we were to consider the full interlaced spectrum of eigenstates in an ordered spectrum of eigenstates in the even and odd sector together, we get a fat tail of very small level spacings. There is a bunching up here, which is due to numerical, finite numerical precision, but otherwise we can resolve these spacings quite well. Now, it is very unlikely that there are exact degeneracies between the sectors of opposite symmetry that we can't resolve due to finite numerical precision, I would argue. There's also a power law, so that the tail does actually look like a power law over the range of spacings that we can resolve. And now, having this knowledge, we can explain why previous studies found sub-Poissonian level statistics. That will happen if you compute the level statistics in the zero magnetization sector without resolving without resolving the inversion symmetry as well.
What does it mean, sub-Poissonian?
So the average of the R value is much lower than Poisson. And I mean, it indicates that there are degeneracies or quasi-degeneracies at least.
Yeah, right. I mean, it's completely meaningless. Yeah. Okay.
Yeah, exactly. Yeah. All right, but it behaves fine, as I showed before, if we compute the spacings within a definite inversion symmetry sector. Okay, sorry, what's happening? All right, now this is a bit qualitative, but here I'm zooming into the spectrum. This is the many-body spectrum for system size 18, gamma equal probably 2.5. And where the red dot is here, I zoom in on the right-hand side, and you can see that there are states of opposite parity. So the blue crosses are even parity sorry, not parity, inversion symmetry sector. The pluses are the odd inversion symmetry sector. So you can see that there are a lot of pairs that are well separated in energy, but then the pairs themselves are, sorry, the pair, within the pair, there is a very small splitting, which is in line with the plot I showed before. It's not perfect, but for the bulk of the eigenstates, this seems to hold. Now, at infinite time, we resolve the small energy differences between these adjacent pairs. And on average, these states will contribute order L squared to the mean square displacement. However, at finite times smaller than the splitting between these, their contribution will on average appear localized. And that's an observation that we have, that the symmetric or antisymmetric superposition of these states does look localized, does look pretty much like the eigenstates in the finite magnetization sectors. And only at large times will this superposition, will the their coherent superposition decay sufficiently that their contribution becomes delocalized. All right, so we can rule out exact degeneracies in the zero magnetization sector from our numerics with good confidence, and we provided an analytical argument for why the zero magnetization sector is fully delocalized. Now, this seems to be in contradiction both with the results we have for the mean square displacement in finite magnetization sectors, as well as the other measures of delocalization we discussed before. Now, let me mention that the Neal state itself is even under inversion symmetry. So the small level spacings between even and odd symmetry sectors are not affecting expectation values for the Neal state at all. So that could explain why we observe similar phenomenology for the Neal state and the level spacings, even in the zero magnetization sector. All right, now it could be that maybe sigma squared, the mean square displacement, is not a good measure of delocalization. in these systems. And here I'm showing a motivation for this claim. This is the profile of the spin-spin correlation function at infinite time, rescaled by the square of the distance to the center in order to show the contribution actually to the MSD at a given lattice site. And as we go from weak field to strong field, we observe one striking observation is that there are areas of or lattice sites where this profile is negative. This is not usually the case in systems that have quenched disorder, for example. Sorry, systems without a linear field and but with quenched disorder. And you can also, well, there's a few things we can see here. For weak field, I'm in all the cases, I'm plotting different system sizes with different line styles. So for weak field, as we increase the system size, we observe widening of the spread of the spin excitation. And so this is in line with delocalization for that value, for that strength of the field. Now, as we go to larger field, such widening is not apparent, but what is apparent is that the profile does not decay very fast, at least. And this is a larger jump here in the field strength, the overall envelope of this is not changing drastically either. Now, if we compute the second moment of this quantity, the negative and the positive parts will cancel each other out, which leads to the plateauing with system size that we've seen before. Now, looking at this as a function of system size, we see pretty strong growth even for, well, we see weak, let's put it this way, we see weak growth of the signed, sorry, I messed this up. Now we introduce, in order to, well, the second moment will plateau, what if we didn't take the second moment of the correlator, but of its absolute value? Because, I mean, if the correlation spreads, whether it's negative or positive, it doesn't matter, it's still spreading in a sense. Yeah, so now taking the second moment of the absolute value, we see that the growth persists even at a large field, although it does become slower as a function of system size. All right. Sorry, these lines, this would be quadratic with the system size, this would be linear with the system size. All right. So we observe this weak system size dependence, and that could either mean that the system, if it is localized, has a localization length, which is on the order of the accessible, numerically accessible system sizes, and only weakly depends on gamma. Or it could indicate that asymptotically the system is actually delocalized, and other measures then should asymptotically also agree with that statement. Other measures being the level statistics and the Neal imbalance. Sorry. Maybe I should also mention that this is all the observations for the finite magnetization sectors are not strongly influenced by adding curvature or a weak quenched disorder. So the finite magnetization sector is not sensitive to the field being purely linear. All right. Now, this opposite sign structure of the mean square displacement has been observed in dipole conserving fractonic models that are delocalized before. And it had the connection to these dipole conserving models has been drawn in the literature, and this is a direction that would be interesting to look into, whether one can derive a one obtains a fractonic model from perturbation theory of the field with the pure field term with interaction and hopping. So this has been studied in the literature, but the connection has not been derived. Just by intuition, in a sense, or comparison of so the effective Hamiltonian, in a sense, as far as I know, has not been derived in the literature, and thus the connection to these fractonic models is not entirely clear. All right. Now, so let me sum up. We observe level statistics and Neal imbalance that indicates localization in both the zero and finite magnetization sectors of the model. However, we have strong numerical and analytical evidence that the zero magnetization sector is delocalized in terms of spin transport. Let me also stress that prior speculation about why the model in the absence of curvature or weak disorder and with only the field term may be delocalized has been based on the argument that the that non-interacting model has massive degeneracies. However, this can't be the underlying reason here, because we observe the, or at least what we observe is that the massive degeneracy should also affect finite magnetization sectors, but it doesn't. So it is likely that this is not the underlying mechanism for delocalization for purely linear field. Also, the reasoning for delocalization applies to any Hamiltonian that has magnetization conservation and that inversion symmetry. So say a cubic potential instead of a linear should also be delocalized in the same manner, unless the spectrum becomes massively degenerate for some reason. All right. Yeah. And this is in contrast with the mean square displacement at in finite magnetization sectors, but we introduced the signed mean square displacement, which shows stronger finite size effects. And ultimately, the contradiction between delocalization and localization in this model could be resolved by just assuming that, just assuming that the discrete symmetry is the sole reason for delocalization, and it's in a sense an artifact of the zero magnetization sector, or that the results are not asymptotic for the level spacings and then Neal imbalance, not asymptotic in terms of system size, and stark MBL does not exist in these models. All right, that was it. thanks for listening, and thanks for the invitation as well.
Okay, let me just stop